We're going to talk about Lab 1 in this video. I'm going to go through some of the leading examples here, work through them, hopefully with you, pull up your lab and feel free to follow along. And I just want to explain some of the basics of what we're doing, why we're doing it. That way, when you get into the problems that you're going to be working on, hopefully you'll have a bit better of a context of what's going on. So definitely feel free to read through all the instructions on here, but I'm just going to talk through most of the basics so that you can understand what's happening. Notice that I already made a copy of this into my drive. I renamed it, so I am going to be able to save things nicely here. Make sure that you do that before you share it with me and before you close out your lab. I can add in my name and due date. Feel free to do that. I'm going to skip past this, though. Make sure that your name is in the title and somewhere on the lab so I can see it. All right, so here we're going to be talking about some integrals. We're going to look at area between curves. We're going to do some volume things with disks, washers, and shells, and then lastly we'll end off with surface area. I have examples of some area and a volume using some washers, and so I'll let you figure out shells and surface area on your own, but you'll see how it goes. It's not going to be too bad, hopefully, to extend from the examples that we have. I'm going to take a look at these two functions, sine of x squared and 2x. There's a little note up here that might be interesting to read. Hopefully that's helpful. And we're going to look at the interval from 0 to 2. We're going to notice that 2x is greater than sine of x squared. So when we set up our integral to find the area between these curves, 2x is our top function. Sine of x squared is our bottom function. We want to integrate this. Again, there's a note that says, wait a second, we can't integrate this. So let's go ahead and check out the Riemann sums. That's what we're going to do here. I'm going to run my little chunk of code here that's going to import NumPy and Matplotlib. And we should be good to go. All right, now we'll be able to call all those functions from NP and use the plotting library and all that kind of stuff. I'm going to set things up a little bit maybe differently than you might expect, but hopefully you'll see why in a second. So I'm going to build this interval from 0 to 2, but I'm going to use some variables. I'm going to call 0a and I'm going to call 2b. That way, if I need to change things later on, I can just change those right here. So I'm going to go from 0 up to 2, and you notice I'm setting up this list of x values, right? I'm going from 0 up to, but technically not including 2, but my step size is so small that it's not going to matter. This is just for plotting these curves. I just want to make sure I have nice, smooth curves on here. So now I'll define the actual functions. Remember that the sine function comes from NumPy. We'll use the double asterisk for squaring things on the inside of that sine function, and then our g of x function was just 2 times x. Now we'll remember how to plot things. It takes in x values and y values here. These are lists of x values and y values. The x values are the things that we defined, and the y values are just those x values plugged through these functions. I can plot both of these at the same time, give it a nice title, and this is what it looks like. We can add more stuff to this graph. It might be nice to have a horizontal axis through here to see what's going on. We will add some more stuff in just a second, but let's get into that right now. We're going to go through a whole bunch of setup on here. I would encourage you to read through all of this. This is just going to explain what my code is doing, what all these variables and things are representing, but you'll see it here and I'll kind of talk through it as well. I'm going to set n equal to 20. That's going to represent the number of rectangles that I'm using. Since I already have b saved, you can notice it says, hey, this was 2, and a saved, that was 0. I can set up delta x by just saying, okay, my normal formula for delta x is the far endpoint minus the beginning endpoint divided by the number of rectangles. So b minus a over n. That's going to give me my width of each of the little subintervals. I can use that to build a partition. This partition is a list of x values that's separate from the list of x values I used above for just plotting my curves, because these are the ones that are going to represent my rectangles for my Riemann sum. So I'm going to use a left sum. This NPA range function is really great for that because, like we said, it's going to count from a, 0, up to b, 2, but remember, it doesn't actually include 2. So we can print out this thing if you'd like to see it, just to see what is this list of x values. And then I'm going to go ahead and I'm going to plot my curve. Notice I'm using the x values from above. That was the really, really fine list of x values, not the partition. But then I have this plot bar. I'm just going to show you the graph first, and then we'll see what happens. All right, so first, here's our partition. Notice that we're counting up by 0.1s. That's what delta x is, which makes sense, 2 divided by 20. And you'll notice that we don't actually get to 2, so these are the leftmost x values from those subintervals. And here's our picture. We got these nice rectangles. Let me show you the code for it, and we'll talk through what they do. If you hover over plot bar, I think you might have to type something. There we go. It's going to pull up a list of all the different things that it takes in. It takes in x values. That's going to be our partition. That's going to be the location of these bars that we're plotting. It's going to take in heights as our second argument. The height is going to be the difference between the two function values at each x value. So it's g of x sub k star minus f of x sub k star. Instead of using x sub k stars here, we have a list of x partition that represents all of those x sub k stars. We need a width. This is a lot of times used for like bar graphs, and so they have a set width that's default in here, but I'm just going to change it to delta x because that's what we want it to be. Bottom, I think it's default at y equals 0, so I wanted the bottom of each of the bars to touch on my function f of x, so I'm going to put the bottom at f of x partition. And then down here, we've got alpha equals 0.2. That's a transparency for the bars just to make it look a little nice. We have the edge color being blue and the alignment being edge. I could change this to center, and it'll line up all of our bars where they touch the graph in the middle of the bar instead of at the edge of the bar. But since this is a left partition, I'm going to use this edge. Most of this stuff, you're not going to change. You're going to set up a list of partitions. You're going to have one or two functions, depending on what you're looking at, to define a height. You'll have to figure out what your bottom is, whether it's y equals 0 or whether it's a function, but that's pretty much it. Again, read through the instructions above, and hopefully that'll give you a bit more details and ask some questions. But that looks like a pretty good little Riemann sum, right? Now what we might want to do is just approximate that area. And this is where we actually get into the math involved, right? We have this formula for our area between curves. It's 0.1, which is delta x, times the sum from k equals 1 up to 20, because there's 20 rectangles, of g sub k star minus f sub k star, or x sub k star, g of x sub k star minus f of x sub k star, where those x sub k stars are the partition values. So we can go ahead and just follow this through. We've got our delta x, that's 0.1. We're going to multiply that by the sum of g of x sub k star, but that's really our x partition, minus f of x sub k star. And we'll just call that thing area and print it out. That there is exactly the area of all these rectangles added up, and approximately the area bounded between these two curves from 0 up to 2. Okay, so let's say we want a little bit of a better approximation. We can change this to use 20 rectangles. Notice I don't really need to change too much. I'm going to change n equal to 200 because we're going from 20 up to 200 rectangles. I have to reset delta x because I've got a new value of n, so I'm just going to resave delta x as still 2 minus 0, but now it's going to be over 200. I'm just going to print that out for us so we can see what it is, just to confirm. And then I'm just going to copy and paste my partition, because I have to redo that with a new delta x, and this area formula down here. Since I'm changing n, I'm going to update delta x, I'm going to update my partition. This area is going to be a new one where we had 200 rectangles. And so you can see, okay, yeah, our delta x did change from 0.1 down to 0.01. That's good. We don't really need to print that out, but I just want to confirm that with us. And this is our new area approximation. So our area approximation went from like 2.96 up to 3.2-ish, right? And you could, again, look at the picture. You can see that there's some kind of error in here. If you like, we can go ahead and replot this picture now. Let's just take a look. I'm going to grab all this. I'm going to copy it, and I'm going to go back down here after we've defined our partition. So now this is going to be using our new partition. It's going to have our new Riemann sum set up. Here's our picture now. That looks like a way more accurate representation of the area bounded between these two curves. And I'll leave it up to you to start thinking about how we might get an even more accurate representation. But let's shift gears now from area to volume. I'm just going to do one volume example because I think if we do one, you're going to see how things work, how they're really similar to the area one above, and we should be able to go from there. I'm going to look at the same functions, sine of x squared and 2x, but I'm going to revolve these around a horizontal line down at x equals -1. So I'm going to go ahead and use 20 rectangles again, just to get a nice little picture of what's going on. So all I'm really doing is resetting n to 20 from 200. I have to redefine delta x and the partition, and then I'm just spitting out this plot stuff. I'm also adding this line right here. This is going to give me a horizontal line at the y value of -1 from x equals 0 up to x equals 2. Let me run this and I'll show you why. This is our axis of revolution. Again, in the instructions above, it explains a little bit more about what this h lines thing is. It takes in a y value, -1, a starting x value, 0, an ending x value, 2, and then I just change the color so it looks nice. But this is what we're going to be revolving around. So you can see that we're going to have some washers now that we're going to be spinning around this thing. We're going to have to figure out some extra radius because our x-axis is actually over here at 0. And we're going to be counting and measuring our radius all the way down to y equals -1. So that means that, just like you would expect, there's going to be this extra +1 in each of our radii when we square them. This is our washers formula that we've got set up for 20 rectangles. And notice that we can just go ahead and write that down in code. Pi times the sum of g of x sub k star, that's our x partition, plus 1 squared, minus f of x sub k star, or x partition, plus 1 squared. Make sure that your order of operations with parentheses and everything are good, and then we can multiply the whole thing by delta x. I'm multiplying delta x technically on the outside of this sum, but it doesn't really matter because delta x is constant, right? And so it's a coefficient that we can factor in and out of that sum. Doesn't really matter. Hopefully that works out pretty well. There's our volume. Cool. If we revolved that region around that axis and looked at that surface, it would have a volume of 47.5, units cubed, whatever. This is just an approximation of our volume, and that's all we can really get, but we can get a better approximation for our volume. Using, instead of 20 rectangles, let's use 2,000 rectangles here. I'm not going to draw a picture of this, but you can kind of visualize what these cross sections are going to look like based on what we had with the area example above. Notice again, I'm just changing n to be 2,000, updating my partition and delta x, and then spitting out the exact same volume formula. But now I get a volume of 51.3, a little bit different. All right, again, I'll let you think about these and which ones you're going to trust more and all that kind of stuff. But this is what we're going to be doing as you move forward. We're going to take a look at volumes using washers and shells, and we're going to look at surface area on here. But notice that you're really just going to be working from this Riemann sum formula that we have to try and write that down. Build those partitions, set up your delta x value, all in the same way that you would normally in these examples, but you're going to notice that the integral formulas are going to be a little bit different based on the tasks that you're doing. Hopefully that's helpful. Good luck as you're going through it, and let me know if you have any questions.